I'd like to take a closer look at the results that we've obtained from using the data analysis add-in, the regression add-in. Before I do that, I briefly make some space here and copy the data again here. So the first thing I would like to make clear is how do we compute the values on the line? And the values on the line are also called fitted values. And they are obtained by using, as the formula in that diagram says, by using the slope multiplied by the living area plus the intercept. I fixed the slope and the intercept so that I can copy this formula all the way down. And now the important thing is any point on that line, so of course copy paste that into the diagram, we see that for every red dot here corresponds to a different living area, corresponds to a different house. So for any value of the living area, we obtain a corresponding price, which has the nature of being an average price for houses with a living area of a certain size. And this average price is not only a local average conditional on the living area for each and every value, it is also kind of an average that summarizes all the data in that sample. Now, these results that we find in here, let me explain them one after the other. The first is the multiple R. Now, the multiple R is the correlation between the sales price observed and the fitted values. And for a simple regression with just one explanatory variable, that is always the same as the correlation coefficient that we've already obtained before. So the correlation coefficient between the living area and the sales price is the same as the multiple R, but that's only the case if there's a single explanatory variable. In general, it's always true that the multiple R is the correlation between fitted values and sales price. The R square is simply that multiple R squared. The usual interpretation of the R square is it gives us the percentage of the variance in the dependent variable, so the variance of the sales price. That percentage is explained by the variance in the living area. So the basic idea here is to say, well, we do have a variance of the sales price, whatever that might be. That variance is the variation, measuring the squared deviations around the mean, the average of the sales price. And now, if we wonder why is there such a variance in the sales price, we could say, well, it's maybe due to a certain extent to the living area variation. So if there's variance in the living area, a part of that variance in the sales price can be explained. And the R square of about 9% says 9% of the variance in the sales price can be traced back or explained by the variance in the living area. So this is a very common and very frequently used measure for the so-called goodness of fit of a regression, R square. The main drawback of the R square is it's measuring that degree of explanation that we've obtained in terms of the variance. So it's measured in, or it's related to the squared units, which is usually a bit difficult. So I prefer to rather look at this value here called the standard error, and I prefer to call it the standard error of the regression, because we'll see later on that there's also standard error down here, and it must not be confused with that standard error in that lower part of the table. So Let me explain what this standard error here refers to. And for that purpose, I compute what is called the errors, or also called residuals, which is simply the deviation between the observed sales price and the fitted values. Just to remind you, both the sales price and the fitted values are measured in dollars, so also the errors are measured in dollars. So in other words, we see now for each and every price and each and every house whether or not the actually observed price is above or below the fitted value. So here we find a house which is actually more expensive than we would expect, and this expectation again is based on the entire data set here and the summary measures, mean, standard deviation, correlation, etc., slope, intercept. Now, these errors are very important, a very important source of information about the quality of the regression. Obviously, the larger the errors, the worse the regression. The smaller the errors, the better the regression. Now, in order to obtain a summary measure for the magnitude of the errors, we might consider computing the average of the errors. And what we get is 0. So what this means is the average error is 0, that the regression line has been fitted in a way so that the observed price is above the line and the observed price is below the line. These deviations exactly cancel. But we can't use the average error as a measure for their magnitude. Instead, we could consider computing the standard deviation of the errors. And now this number is about 51,000. And it should be noticed that this 51,000 is what is produced here in this summary table from the using the add-in. So the 51,600 here and the 5700, these are actually measuring the same magnitude of errors. There are technical reasons which should not bother us for this difference. If the sample size increases, that difference becomes smaller and smaller. So what is more important is the interpretation of that standard error or standard deviation of the errors. In the same way as the standard deviation of the prices measures the dispersion around the average price, the standard error measures the dispersion around the regression line. So we're considering two different standard deviations. One measured against or around the mean, the overall mean, and the second against the sloping regression line. And that difference between those two numbers shows us to what extent we were able to make use of the information in this living area. Because if it's the case that as a tendency, smaller houses with lower living areas are cheaper and have a lower price, and larger houses with a larger living area tend to have a higher price, that information enters into that sloping line. And the dispersion around that line gives us an idea about the role and the effects of potentially other explanatory factors. But what we have achieved so far by accounting for the size in terms of the living areas, we've reduced the original dispersion of about 53,000 to something like 51,000. And that comparison is a very important comparison. First of all, it can be made in terms of dollars. It can be made in terms of the units of the variable we are primarily interested in, namely the sales price. And we see we have reduced, by accounting for the size, we have reduced that dispersion by about $2,000. But still, we have to face a dispersion that we cannot yet explain of about $51,000. So this is an immediately telling number. What is still left to be explained? Which orders of magnitude are left to be explained? Now let's compare that information to the R-square, which is a very frequently used measure for the goodness of fit. Now the R-square says 9% can be explained by accounting for the living area, but 91% is yet to be explained, is left unexplained. Now, but this 9% or 91% refer to the variance of the sales price. And it's very hard to relate to the variance of something because it's measured in squared dollars, in this case, squared units of the dependent variable. Much more informative, according to my mind, is a comparison of standard deviations of the dependent variable of the sales price measured in dollars around the mean. Now, if we account for the living area information, we're able to reduce that by about $2,000, $3,000. So we get information in terms of dollars, and we're left with about $51,000 yet to be explained. Now, obviously, this is still a big challenge. We are left with a lot of dispersion that cannot be traced back to living area. It must be due to other factors. And in my videos on multiple regression, I will show you how to include further explanatory variables. And with those, it should be able to reduce the standard error of a regression further than here.